Hi there. In this video, we're going to be looking at how to evaluate multiple integrals. If we think back to single variable calculus, we looked at how to calculate the area underneath the curve. We saw that if you have some kind of random curve and we wanted to compute the area underneath it, what we did that was we broke it into little strips. We could have a little strip like that. And the width of the strip would be the length delta x, and the height of the strip would be just the value y, as it is just the y value. And then we looked at taking this strip along the entire part of the curve which we wanted to determine the area underneath, and then we added all of them up. So adding all of them up, it's the sum of the area of one of these strips. So that length is delta x times y. So if we now consider this in terms of a function, and then we consider these little strips as becoming infinitely small, then this delta x approaches dx as this delta x becomes very small. So this summation sign becomes replaced with an integral sign. So the area underneath the curve becomes the integral between the two parts of the curve, for example, x1 to x2, and summing up all of these different strips. So we just get y dx from x1 to x2. So the idea now is to extend this into more than one variable. So we'll start by looking at the area of just a shape, still in the Cartesian plane, and still 2 dimensions. So from a single integral, we're going to go to a double integral. We could have some kind of shape, and we look at a little, just a little square inside the shape, and the width is delta x and the height is delta y. So if we're now wanting to sum up this little square over our entire shape, we have to add it up in 2 dimensions. We're going to have to do it firstly across the x dimension, or along the x plane, carrying on like that, and then also extending this entire thing along the y-axis, and that will give us the entire shape of the area of the shape. So doing our summation, we're summing up all the little bits of delta x and delta y, and this is of course a double summation. So if we let delta x and delta y both to approach 0, then they become dx and dy, as was the case before. And instead of this summation sign sigma, we have 2 integrals going from x1 to x2 and y1 to y2. And of course, it's dx dy. So the way in which this type of integral is actually calculated is by looking at, firstly, one of the integrals, evaluating that. We'll call it the inside integral, and then evaluating the outside integral. So we do this part first, the inner, and then we do the outer. I think this is most easily illustrated with the use of a simple example. We would like to calculate or evaluate some kind of integral, which is a double integral, where there's 2 bounds for each integral. In this case, the outer integral is going from 1 to 2, and the inner integral is going from 2 to 4. And we are evaluating the integral of the function x plus 2y dx dy. So as I've just stated, the technique is to evaluate the inner integral first and thereafter the outer integral. So if we're doing the inner integral with respect to dx, what it means is that we're treating y as a constant. So we're only integrating with respect to x while treating y as a constant. So we keep the outer integral as is, and now we integrate what's inside. So the integral of x with respect to x is a half x squared, and the integral of 2y, where 2y is being treated as a constant, and therefore that is 2xy. So just the derivative of x becomes 1, and then you're left with 2y. And then this is being integrated from 2 to 4. Since we have already integrated with x, we can remove that dx. So we will just write dy at the end. We now evaluate this integral as we've done in all previous cases. We would just substitute in 4 and then minus, then after substituting in 2. So doing that, we leave the outer integral as is for now, and then we substitute in 4. So 4 squared is 16, and 16 divided by 2 is 8. Then substituting in 4 here, we have 2 times 4 times y. 2 times 4 is 8, so we're left with 8y. So now we subtract, and then we substitute in the lower bound. 2 squared is 4, 4 divided by 2 is 2, and then 2 times 2 is 4. That would be 4y. And we leave the dy as is for now. And then we simplify it. So 8 minus 2 is 6. And 8y minus 4y is 4y. So we now integrate this with respect to y. So that gives us 6y, the first term, and then y squared. So what times y squared gives us 2 times what gives us 4, and that's 2. So the integral of 4y is 2y squared, and we're integrating this from 1 to 2. Substituting it in as we would usually do. 6 times 2 is 12, and then 2 squared is 4. 4 times 2 is 8. Then we have minus, we just substitute in 1. So we have minus 6, minus 2. So 12 plus 8 is 20. 20 minus 6 is 14. 14 minus 2 is 12. So this is a simple example of how we would integrate a double integral. So the technique is just simply to do the inner integral first, thereafter the outer, and when we're doing the inner integral, we would simply keep the other variable constant. So we're now looking at triple integrals. We would need to draw our figure in 3 space to be able to show this. So a triple integral of a function would typically give you the volume of that specific function within a particular region. So we could have a 3-dimensional cube, for example. So we would have 3 axes, that would be the x, y, and z axis, and we would have our shape, a 3D shape. And within this 3D shape, we can isolate just a little section, and we could have a 3-dimensional block, a volume block, as we would want to think about it. There's our little volume block, just as we had a little volume area. This is now a volume block that we will be integrating. So that's delta y. This is delta x. Sorry, my apologies. That's delta y, that's delta x, and the height is delta z. So we sum up this little block in 3 dimensions. It would have to go up, it would have to go along the x-axis, and along the y-axis as well. That's the y-axis. So if we wanted to compute the volume, we would have 3 summations of delta x, delta y, and delta z. And then, of course, if we let delta x, delta y, and delta z approach 0, and it becomes dx, dy, and dz, then we have the triple integral of dx, dy, and dz. And then this is computed over some region. So the way in which we would solve this, or we would calculate it, is by doing it the same way we had done the double integral. So instead of one inner integral, we have two inner integrals. We would do the integral with respect to dx, then with respect to dy, and then lastly we would complete it by integrating with respect to dz. So we can illustrate that with a simple example, and that example is to do the integral evaluated of, we have three integrals, three bounds. So integrating from -3 to 3, from 1 to 3, then -1 to +1, and then from 0 to 2. And we're integrating the function x plus 2y minus z. So we would do it with respect to x first, and that means leaving the rest of the terms as is, the rest of the integrals. So we would keep it from 1 to 3, -1 to 1, and then integrating with respect to x, we have a half x squared plus 2xy minus xz. And this is from 0 to 2. And since we have now integrated with respect to x, we just left with dy and dz. So if we substitute in 2 and 0, what we're left with is still the same integrals as they were. And substituting in 2, we have 2 squared divided by 2, and that gives us 2. And then we have 2 times 2, so we have plus 4y. And minus 2 times z. And of course, substituting in 0 leaves us with no terms, as each one has x in it. So then we integrate with respect to dy and dz. So now we do the next inner integral. So that's the inner integral from 1 to 3. Then integrating with respect to y, we get 2y plus y squared, 2y squared, 2 times 2 gives us 4, minus 2yz, integrated from 1 to -1. So now we substitute in these two bounds. So the outer integral remains the same. We now substitute in 1. So 2 times 1 is just 2. 1 squared times 2 is also 2. And substituting in 1, we left with minus 2z. Now we minus 1 times 2 gives us minus 2. Minus 1 squared is 1. So we still have plus 2. And minus times minus gives us plus. So we have plus 2z. And all of this is still going to be integrated with respect to z. Simplifying this, 2 plus 2 is 4, minus 2z, and minus 2 and plus 2 are going to cancel out. So we have minus 2z, so we're left with minus 4z. So now we integrate this. The integral of 4 is just 4z. We have z squared. So that gives us 2z squared, and integrated from 1 to 3. So it's just a simple matter to compute this. 4 times 3 is 12. 3 squared is 9. 9 times 2 is 18, so you have minus 18. And then with the 1, 4 times 1 is 4. 1 squared times minus 2 is minus 2. 12 minus 18 is minus 6. Minus 6 minus 4 is minus 10. Minus 10 plus 2 is minus 8. So this is a simple illustration of how we would integrate multiple integrals, that is double integrals and triple integrals. So just one final point before this video concludes is that we can reverse the order of integration. If we have a double integral that's going from y1 to y2 and the inner integral from x1 to x2, dx, dy, we can actually reverse this order of integration. So what this means is that the outer becomes the inner and the inner becomes the outer. So this can also be rewritten as the integral with x being the outer integral. So it's going from x1 to x2 and y going from y1 to y2, dy dx. So we would integrate with respect to y first and thereafter integrate with x. So in both instances, we would get the same answer.